Hello and welcome. Here we are in lecture 4. So we're picking up where we left off last time. Last time, remember, we did combinational logic and combinational circuits in Chisel. Today we're going to do sequential circuits. That is, circuits that have state, that have memory. And so we're going to talk about how to do that in just a few seconds. And so today we're going to have a lot of fun kind of showing how to incorporate registers into our designs. Later on, we'll talk about memories as a large collection of a state, but for now it's just a single register or two at a time. And we'll also talk about waveforms and other things that might help with debugging and kind of getting more familiar, more comfortable with the language. Okay, so as said, today we're working on registers, talking about sequential blocks, and of course put the two of them together to make state machines. Great, so let's go ahead and load things up. And fortunately, it's working okay without Wi-Fi. And so let's talk about registers, right? So registers, of course, are how we store things in hardware. And usually we think about just the thing on the right. Oh yeah, we have a register as an input and output. Perhaps in your hardware class, you saw this labeled as D and Q. But of course, we know that there's a lot more things to it, right? Of course, the register has a clock. It determines when it reads input. So for Chisel and for this course, we're working exclusively what they call positive edge-triggered flip-flops. That is, when a clock is on the rising edge is when we read the input. Otherwise, it ignores the input, and then the output is continuous for the entire cycle. Now, when you have a register, there's various bells and whistles you can have on it in terms of does it have a reset port or the ability to have a write enable. And so for those various cases, depending on your technology library, different ways of doing it. On this diagram on the right here today, I'm kind of showing abstractly and kind of theoretically how it looks. It turns out, of course, we put this in real hardware. These may actually not be muxes. They may be specialized form registers. But you can think of it as, qualitatively having this impact, right? For example, if I have a reset signal, it doesn't matter what the input register is. The reset value is the value that can get set to whatever that value reset is. Or for example, if I have a write enable, if the write enable is 0, it doesn't matter what the input is. I'm going to keep storing the same value I had originally. After the write enable is on, then of course it takes the new value, the next value. And so let's talk about how this appears in Chisel. So in Chisel, when you want register, you say, hey, I want register. You declare reg and then the type inside the register, right? And so this is kind of a bit different from Verilog. If you've written Verilog, you write behavioral Verilog, and technically an always block. And then the way you write it, the CAD tools inferred that should be accomplished by register. So it's kind of a little bit indirect. In Chisel, they removed ambiguity. It's just you want register, you declare, hey, I want registers. So as we said before, right? When somebody think about Chisel, really all you're doing is just instantiating things and connecting them together. So here's a case of you instantiating something, a register, and then of course, how you place the designs, how you connect it, right? And so what's interesting about that is with that perspective, there's not really magic registers, right? It's just another hardware block, right? Versus, in Verilog, when you think of a register as special, okay, it's a sequential block or something. No, it's just another block. I have a mux, it's a piece of hardware. I have a register, it's a piece of hardware. I instantiate it, connect it how I want to. And then also remember, of course, in Chisel, that the clock and the reset are implicit. We actually don't need to declare them in the code. They're all kind of passed around automatically between modules, and they kind of do the right thing. Occasionally, maybe not occasionally, rarely, but a few percent of the time, you may want to change that. You may want to have different clock signals, maybe have a custom reset signal or something. Or in some cases, for real hardware, you may want something called an asynchronous reset, and a reset that works asynchronously relative to the clock. Chisel supports that. I linked to some of the things in the docs here, but that's both not only not today, but also probably not only needed for this course. You'll probably be able to do the entire course just fine with the implicit clock and reset. Cool. I'll show some code examples in a second. If any questions so far. Okay, well then, let's go check things out. So here we have a trivial module, just as a place for us to kind of try out some stuff. And we're going to show different ways of declaring registers, right? So we have, in this case, a input and an output, and then a write enable. You're going to see in the beginning, we're not going to use that. So for example, in the most simple case, we're just going to declare a register. And when you declare register, you give it the type of what it's holding. In this case, bool, so 1-bit thing. We connect the input of the register to the input of the module, and the output register to the output of the module. And then to go ahead and pass this through to get Verilog, this is perhaps what you expect, right? So in Verilog, using always that positive block in this case to make a flip flop, and it uses a reg variable. And despite the name being reg, a reg in Verilog is not guaranteed to be registered, right? Just the way it's used in the always block. That's in contrast to Chisel, where it said when we say reg, it's actually registered. You're saying I want this hardware. There's no ambiguity. You're getting a register. Cool. Okay, so that's a simple register. Connected it in there, no problem, right? Now, if we want to be a little bit more sophisticated, we could have a register that has an initial value. And based on the initial value, it can infer the type of what you're going to be holding, right? So in this case, it's going to be holding a bool, so it knows that. And so you say, hey, our register is going to have a reset value of 0, right? So yeah, sure, it generates the Verilog where if reset's true, we're going to set it to the value. Otherwise, we're going to set it to whatever the input is. Okay, not too crazy. Of course, could change this to be, a 1, and then this register resets to 1, and the code generator is being a little clever here. It realizes rather than saying, if that's 1, right, if resets 1, you're resetting it to 1, well, then you could just actually use reset directly here. It's kind of a little clever logic trick the tool did automatically, but it's the same hardware, or same function, I should say. Another thing to point out is that sometimes when you do things in the Chisel or Fertile tools, before you emit the Verilog, even if the Verilog seems not perfectly optimal, remember that the Verilog-based tool, whatever your CAD tool is also going to optimize things too. And so one of my core themes, of course, is let the tools do the work. And so in this case, right, if you use a human set around thinking for a while, maybe you can think of this optimization, but you know what, the tools did it on their own, and that's great. My job is to make correct and clear hardware and then let the tools do the work, right? And so yeah, okay, cool. So that's us doing with initial value, but of course we can set it back to 0, no problem. So these are kind of the ones you probably use the most, or reg init. But there's some other ones people also use. And so let's go ahead and try them out. But maybe I'll pause for any questions so far. Yes. Active low reset. Great question. In that case, you're going to want to do multiple clock domains and have a neg clock. Yeah, so let's be clear, right? So there's edge triggered flip-flops, which is what Chisel works on, in particular positive edge triggered flip-flops. And so to do a negative edge triggered flip-flop, you would want to have a clock inverted to then get the negative edges. So that way, it's still positive edge from the point of view of the clock, it's just a negated clock. Now, perhaps what you're asking is, rather than a flip-flop, maybe I want a transparent latch. That's something that's actually not in the language, right? Chisel assumes you want positive edge triggered flip-flops, does not have latches, and it turns out a lot has been built without latches. Now, maybe you say, I really, 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 really need latches. Guess what? That's okay. So in Chisel, there's a functionality called a black box. We're able to take any Verilog or VHDL you would like, and then write that, and then have that appear in Chisel. You can call that. So you can instantiate that module. And so this has kind of been an escape hatch just used in a handful of scenarios where sometimes in an industrial application, they have a certain macro they want to use, right? They don't want to just write Verilog. They want to have the exact Verilog snippet that their tool needs to do a certain thing. Like, you're writing on FPGA and they want to explicitly instantiate FPGA's DSP hard block or something, right? In which case, the exact Verilog snippet you want to instantiate, right? So in that case, yeah, you can use a black box where you can put that Verilog inside a black box and you can instantiate that black box and get what you want. So when it comes to registers and latches, people have had the situation where a lot of real chips use asynchronous reset. And so they were the ones that were pushing for that. So that was a very commonly instantiated black box. And it was so common that in one of the revisions a couple of years ago, they made asynchronous reset now part of the language. But great question. Yeah. And so then for latches, I would put them inside of a black box. Yes, question. So what would be wrong? Yeah. So to clarify, so there's two things you can do, right? So when you modify these things, you can make things explicit rather than implicit, right? So you can say, no, no, don't use the global implicit reset. Use this logic signal I've manually constructed, which has certain constraints to it. That's one option. In the case of asynchronous reset for registers, actually a way to do it. So we go ahead and click on that link, and we can see the, oops, Wi-Fi come back to bite us. But other than that, you can see that, right, there's a little bit of syntax and clarity through a little differently. When it comes to multiple clocks, you actually mark the scope for the other clock domain. Like, oh, this is clock domain A, this is clock domain B, and you can kind of describe that. And you're supposed to use, special devices to go between clock domains. Well, yeah, so the easiest way to do it would be to lead register alone. It's still a positive edge triggered register, but then you just have an inverted clock. So that way, what was a neg edge on the original clock is a pos edge on the inverted clock, and that's what you pass it to register. So it's still a pos edge triggered register, but it's being fed the inverted clock. So now you've made it effectively a negative edge triggered flip flop. Yes. Maybe I misunderstood. I'm sorry. If you want to have an actual low reset, it might be one of those situations where you really have to just use a black box. That's kind of that's that. So another way to kind of make this more clear is so chisel as a intentional language choice, rather than optimizing for all these kind of special cases, is assuming kind of modern era Verilog design. So modern era Verilog design latches are used almost never. Everything is synthesized, um, and active low is pretty rare. And so rather than include all these possible options, they made the language simpler, kind of like a risk mentality. This is from Berkeley, and they didn't include that stuff. And so then there are various escape hatches to get those things when you really want them. And it's kind of interesting to watch sci-fi over the last, what, 7 years, see how many of those things they came to miss or did not miss. And it seems like of all those things, the thing they most missed was asynchronous reset. So the latches, for example, are cool and they make sense on paper, but they're hard to make work at 4 gigahertz at 4 nanometer. Um, so that's kind of why they weren't chosen. But I mean, not everybody using Chisel is doing 4 gigahertz to 4 nanometer, right? Maybe we're doing 100 nanometer Skywater, in which case we should be doing latches or something. So, I mean, yeah, this is one of these things where perhaps you will have a black box library internally for your project, in which case you will be happily instantiating these modules. Good questions. Yeah, I'm so happy to have these conversations. It's good to kind of get up. And you can kind of see the challenge of the language design where you have this debate between giving richer functionality to the user versus them responsible for actually implementing and supporting this functionality. And so it's kind of thing about what to do. I feel like over time, most languages and standards tend towards providing everything. And I think that sometimes is a mistake, in my personal opinion. Maybe perhaps too parsimonious, but good point. Okay, let's go back to the registers and see if we can do a couple more combinations, right? So these are the most common things. You probably declare register, or maybe declare a register for initial value, and then you kind of connect it up. But there's actually some of these other things in the standard library to make it easier. So for example, there's regnext, which is kind of like the one we just saw a second ago. So what does regnext do? This declares a register. You pass as an argument to this thing the input. So it's going to construct a register and connect the input to register to that first argument. The second argument is a default value. So it's already going to have a reset on it. And then this whole thing as a register, you can connect to the output. So the output of this register becomes the output of this module. So this whole thing becomes one block. And so perhaps regnext also is a very commonly used form register. And you see the same thing. Like before, if I optimize this one, it should do the right thing and be clever. That's regnext. I say this is also probably pretty commonly used. And then the richest one is regenable, where you have not just the next value, the initial value, but also the enable, right? And so you can kind of see, depending on which of these things you want to declare, it's kind of all there in the preset thing. Yes, go ahead. Okay, great question. So I want to do a 2-cycle delay. Yes, you could do a regnext and then wrap that in a regnext. Definitely. Um, there are other utilities in the standard library to do, like a shift register, multiple registers in a row. Um, so most commonly in the one you're describing is what's called a pipe. I'm actually going to be building things like a pipe manually in some of the next few lectures just to show some of the kind of generative program models. To show, okay, if you want to generate registers in the pipeline, the various ways to doing it for recursion, with iteration, various ways to kind of gain that across. But yes, for the question of just right now, yes, you could just do regnext and then wrap that in regnext, and that'll give you 2 registers in a row. Cool. Great questions. Great. Okay. So let's go ahead and try to put this together and build a counter. And so to be extra clear, there is a counter in standard library. There's a few counters in standard library. We're doing this manually just to get experience playing with this. But in your hardware design, of course, you probably should use the standard library counters. So, a counter is something that has a register and you hold a value and you when told to, it counts up, right? So in this case, we are going to have the output, the current count, and then enable to make it count. We're going to make this a generator. So actually it's going to take in a maximum value. Let's go ahead and run this. And so, or not run this, but generate Verilog for this. So we can kind of see this thing come together. Maybe I'll talk through the chisel first, right? So, okay, so we have the count being held in the register. I'll talk about the sizing in a second. I'll come back to that. The next value to this counter, what's that going to be? Well, it's either going to be the count plus 1 or 0 when we wrap around, when we saturate. Now, sometimes you can be really clever and you can recognize, based on the power of 2, it's going to do the right thing naturally with overflow. You don't need to do anything special. This is a generalized counter, so the maximum value could be something like 4 or 5, something that's like not perfectly aligned, in which case it's going to do the right thing for mux. In this case, our next value is going to be, based on us reaching a maximum value, and otherwise, we're going to do the right thing. Okay. In terms of the other parts of the design, we could then, of course, have our, enable signal. So in this case, I'm doing it very manually rather than using like the reg enable. I'm just doing reg. And so to kind of manually construct the effective enable, we are either taking an X value or the count, meaning we're not changing, and then putting everything together, right? So either we're resetting or this one. So, here we have 3 muxes, if you aren't using very fancy registers, we get this whole thing popping out down here. Okay. I'm going to come back to this issue of register sizing, but for now, any questions on this first version? Yes. Great. So questions about the apply n. So what this is basically just a mux, and we're choosing between, are we going to keep the current value? The current value is the count. So this is a true false case for a mux, right? So if the enable is false, we want to keep the same value and not count. If the enable is true, we want to go to the next value. And next value is either +1 if we're below our maximum, or if we are equal to the maximum, then the next value is going to be 0. Great. Okay, so yeah, this is kind of clunky. If you're looking at this and saying this doesn't look that nice, no, it's not. So let's see what we can do and make this a little bit better, right? So maybe we could use reg init, right, to kind of get rid of one of those muxes, right? So okay, we could use reg init to say initial value is 0. We're still using a mux to do the wraparound because the wraparound might be arbitrary. We're still doing a mux for the enable. But hey, this is, one line simpler. It's one less mux in the code. The output should be the same, just about. But in terms of the code syntax, you can see here we are using that register shorthand, getting a little bit cleaner, a little bit nicer, a little bit simpler. We can keep going with that, right? So we can go ahead and instead of using muxes, we can use whens, right? Talk about whens last time. So we still declare our count, and we're still going to do reg init to get the 0 value for by default, but then this is kind of more clear, right? Hey, if I'm enabled, I'm changing values. If I'm not enabled, I'm not going to change values. So that's kind of handled nicely by the whens, kind of makes that logic very clear. And then, hey, if I'm below the maximum value, I can just increment by 1. Otherwise, I can wrap around. If I'm in a max value, wrap around to 0. And oh yeah, by the way, the output value is going to be count, right? And one thing you might notice is that with this code transformation, I no longer have to have this like variable or wire for next value. So for example, maybe in Verilog, you might have some sort of like next value lot, something like that. Or even the prior Mux example, you had that. But here in Chisel, we actually are expressing all these things as connections to count, and then the logic for processing and synthesizing a when statement is kind of handling that for us. So yes, this one should produce similar hardware. Um, but I would argue this is hopefully getting more readable, what we're doing, right? The kind of intention is more clear here. Okay. And then if we go one step further and say, hey, there's that reg enable thing we had before. So what if we use reg enable and we used a mux inline to do the wraparound? No problem. That can be done. We basically turned that entire module into one line. It should be, once again, the same hardware. I deliberately include this code because personally, this is, I would argue, pretty dense. So actually, this is not my favorite one. I actually would argue the one before is a little bit better. It's a little bit more clear what's going on. If someone's reading this code or trying to modify this code, in this case, we found reg init made sense for our uses, but the reg enable with the mux inline, that was kind of a lot of density, right? And so, yeah, there's a lot of code here at one place. And so if you're trying to, evaluate your code in terms of how useful it is to others, how readable it is, sometimes having too many things in one line, of course, is hard to deal with. And so I would argue that maybe this one's a step too far. And sometimes I kind of do this in the lectures to kind of show the impacts of what we're doing. I'm going to stay on this slide for a second because it has the shortest code, so we have the most space to see the Verilog easily. We'll talk about what's going on down here. So for example, we decided our maximum value is 15, right? So it's going to go 0 to 15, wrap around. 0 to 15, wrap around. Okay, so how big should that register be? Well, it has to be able to hold 15. That's the biggest value we're going to hold. And so I want to be really clear about our terminology here. I'm saying the maximum value the counter holds, right? Because remember, technically 0 is also a value the counter holds. So if I have n as my maximum value the counter holds, really I'm counting n plus 1 things, right? Because there's zeros through n, right? And so, okay, I need to have enough bits to hold that value, right? And so there's some utilities built into Chisel if you would like to use them. For example, a common one is log2 seal or log2 sealing, which if given a number tells you that number taken log2, round up to the nearest integer. And so in this case, this is what we need, right? We want to know how many bits is it going to take to hold this thing, right? So and how many bits would it take me to hold 15, for example? And so we're going to see, oh yeah, that takes 4 bits, so it's 3 colon 0. So we're going to kind of size that thing appropriately. Cool. Questions? So for example, if I change this, let's say I make this like, 0 might break things. Let's try something simpler like 2, right? So 2, I'm actually going to need to use 2 bits because it needs to show 0, 1, 2, 0, 1, 2. So I need 2 bits for that, right? So we can kind of keep going, right? It's 3. Okay, 3 is going to still be fine, 2 bits. Now to actually have the value 4, I actually need 3 bits, right? And so that's why we have that plus 1. Okay, cool. And then out of curiosity from the audience, let's go ahead and try 0 and watch it break. It didn't crash, but yeah. It turns out that there's plenty of chisel modules that actually are totally okay with certain parameters that you normally think make no sense. And actually tools do their best to go forward with it. And so some cases, for example, you can have a 0 width wire, which sounds totally broken, but actually the tools do the right thing. So one place this comes up, for example, is if you have a memory, if you have only one element in the memory, to address that takes 0 bits, right? Because it actually will prune away the addressing logic. And now it's just a register. It can do that. So it's a good question to ask is, gee, do I have any constraints on this? And notice how in my code, I probably should have put a require statement, saying, hey, you better give me a max file greater than 0. But, you need to be a little bit obtuse sometimes to be safe, but you got to put something like that in there. Because yeah, if you put this in there, now it should at least tell me, don't do that. And unfortunately, because of Jupyter, when exceptions are triggered, it just hangs. But uh, we know why that exception's happening, right? Cool. Questions. All right. So we saw test benches last time. Uh, one new function is step, right? Which steps the clock cycle by one cycle. And so when we had our combinational logic tests from last time, as well as you've seen in homework or the lab, um, you can, poke a value, and the simulator is going to automatically simulate any combinational logic, and it's going to change the output immediately. So you can do poke and then expect right away, no problem. If later on you want to, do things like print out the values or look at a waveform, you actually need time to advance to kind of differentiate things. And so for today, you definitely have to use step because we're doing sequential circuits where registers that change every cycle. But even if you weren't doing registers, sometimes you still kind of use step inside your test benches to kind of make time advance so it makes things more clear for the output for parsing it. Right now, we're doing this just running a test case, and we're going to say, hey, look, it passes. At the end of today's lecture, we'll cover both waveforms and printf to kind of get more information out of this. But yeah, I mean, we can see, okay, I'm going to run a test. It didn't give an exception, it passed. So what did it do? Well, for example, we turn enable on. We initially expect the value to be 0, right? One cycle later, this value should be 1, right? Enable still 1, so one cycle later, the value should still be 2. Great. We step a cycle. One cycle later, it should be 3. We turn off the enable, so then one cycle later, it should still be 3, right? And then you can see here, for example, how it goes around. And then this one has a maximum value is 3, so actually enabling on 3 and one cycle later, it wraps around to 0. So this tiny little test bench actually kind of shows this. And so for today, as well as in the first homework and first lab, you can kind of manually write these cases out. As the course goes on, we're going to get better and better at using Scala to actually generate these test cases. So rather than us, manually imagining every single cycle, as you imagine, it's very error prone, very brittle. Instead, what you want to have is some sort of Scala that does programmatically, functionally, the thing you want to be doing, and using that Scala to generate the test cases. So we'll cover that more in future lectures. But for today, yeah, it's very verbose, copy-paste kind of twiddling stuff. Cool. Okay. So, any more questions on the counter? Yes. Oh, good question. So if I repeat the question for recording, if I, omitted this poke, which does the exact same thing as right here, what would happen? Correct. It's going to keep, whenever you poke a signal, it's going to keep poking that signal indefinitely until you tell it otherwise. In this case, I included it every time, even though sometimes it doesn't change, which case it would be redundant just because it makes the copy pasting kind of clear what's going on. But yes, you could definitely, you only need to poke when you change the value. If you don't change the value, you don't need to poke it. Good question. Cool. Okay, so recap. We talked about registers and getting them going. In order to do state machines, we want one more thing to make our life a little easier, and that is enums, or enumerated objects, right? The ability to kind of have nice ways to describe things, right? And so enum, believe it or not, is actually a chisel thing. In Scala, an enum is actually spelled out as the enumeration of the holder type inside Scala. But so in chisel is helpful because we can go ahead and have enumerated things. We can go say, hey, I want to, rather than writing a bunch of numbers all over the place in my code and getting numbers wrong, I can have nice human readable names. For example, maybe names for states in my state machine, and that works out pretty well. Now, as you see, I can kind of see some common uses of enums, right? You can do naming states in state machine. That's what we're going to do in this class. Maybe if you have a more fancy design, you might want to actually label the way a mux way. So mux choose between different things in your data path rather than just being mux way 0 or mux way 1. It can be, actually labeling what each way means, being more kind of explicit, verbose. Or also even just labeling options for interface. You can imagine you have some sort of homegrown, IO interface where you have, an enum for the operation performing. Am I doing a read or a write? And you, rather than saying, oh yeah, it's read 0 or 1, I forget. No, use an enum. That way you just say this is a read operation or write operations, works out together. So if you want to think about this in terms of software engineering, this is what refers the dry principle, or don't repeat yourself, right? So by using an enum, you kind of specify what these values are, and it kind of goes over. So enum is actually one of the older chisel abstractions. There's a new one called chisel enum. Uh, I don't, I'm not opposed to it. I didn't include it in the slides because I feel like it's a longer syntax and the benefits that this other one provides aren't appreciable in this course. So I'm okay with going with the OG one. So go ahead and see this in practice, right? So to have an example to run through this, here's a state machine, perhaps of our unofficial mascot here at Santa Cruz, a raccoon. So what might it do, right? So of course the initial state of a raccoon is going to be hiding. And if it doesn't hear any noise, maybe at some time it'll sneak out and go wandering around. Okay, if it keeps wandering, eventually maybe it finds trash. Great, so it runs through the trash. If it finds some food, it will of course eat the food. And if of course the food runs out at some point, it's gonna go back to wandering. If at any point it hears a noise, it's gonna go back to hiding, right? Um, this is no simple four-state state machine. Let's go ahead and write this up in Chisel. So here we go. So we have, a state register which holds the current state, what the raccoon is doing. We're using that enum to have these nice shorthands for the various states we're going to be in. So for example, to hide, wander, rummage, or eat. So technically behind the scenes, what this enum thing from Chisel is doing, it's actually binding each of these variables, or these values, I should say, to a uint. So it knows there's going to be four of them. So it's a 2-bit wide uint, and this is going to be, uint 0, uint 1, uint 2, uint 3, etc. Let's say, for example, maybe you knew you really wanted a certain value for enums to hold. That's one of those use cases where you should use a new chisel enum. You can easily set, not even necessarily all of them, if you only want to set some of them certain values, you can do that with chisel enum and it'll kind of fill the rest automatically if you need to. So there's some nice examples in this thing linked, which I wish we had Wi-Fi for. I can try one more time and give it a chance in the background. You can see some examples used inside the RISC-V processor using this to kind of to do things like remember certain opcodes for nice data coding, that kind of stuff. Cool. Okay, going back to the code, we have enums for our states. Cool. And then we kind of can just do things based on the state. So for example, hey, if the state is hiding, remember when we're doing chisel comparisons, we use 3 equal signs for equals to differentiate from the memory equality. Yeah, if it's hiding and, hey, if there's not a noise, we change to wander, right? That's kind of like that thing we saw in the prior slide. If I'm currently in a state of hide and there's not a noise, I go to wander. There's no edges departing the hide states. That's kind of just it for that one. However, if it's not in state hide, and let's say I'm in state wander, there's 2 outgoing edges, right? So let's go remind those edges are, right? So it's either there's a noise, go back to hide, and if there's trash, go to rummage, right? So we're making the choice here to prioritize noise. So if there's any noise, yeah, we're gonna go hide, right? And meanwhile, if there's not noise and there happens to be trash, we'll go ahead and go to rummage. So here you can kind of see a case where we have a when, else when, else when. So you can kind of see how sometimes these when constructs, we can kind of handle these cases in a way it's kind of very human readable and like if else you may be familiar from their languages, but we know behind the scenes in hardware it's doing muxes and prioritizing muxes and that kind of stuff. Cool. So okay, so this is us doing that state machine with the when state, which you guys already know. Um, we're only controlling the state variable, right? And then of course the state register is connected to the output, which is our action. You know what we're doing. I can turn this into Verilog. It's a little bit verbose, right? You can kind of see the various things. There's these internally generated signals that kind of uses throughout the design, but you can kind of see based on um, the internals, it's actually filling things based on Gen 1. And what is Gen 1? Well, it's kind of based on all stuff over here, right? So you can kind of see all these cases and the else ones we were talking about, these all turned into muxes, right? Oh yeah, is this input or something else? You can kind of see the next state. Now notice how in this hardware, or in this Verilog, these, state enums have been turned into concrete values, right? So at this point, a certain state is a certain value. I was just joking how if you're a very, very proficient FPGA programmer, you may know how to write Verilog in exactly the right way to make your FPGA tools do optimal state assignment for you. I'm not sure I'll do that in Chisel. I don't think it is easy to do that in Chisel to make the CAD tools do state assignment for you. That being said, there's actually a portion of one of the RISC-V processors um, that does run some things in Scala to try and determine the states on the fly. But in terms of default stuff built in the language, I'm not sure. I think sometimes ones I'm okay saying, you know what, maybe it's a small efficiency hit if I have my 2-bit state machine not having optimal state assignment, but I'll live with it, and go with that. The important thing is kind of get things that work. Cool. Okay, so here we're using when. We could also do something called switch, which is like a switch case that we've seen in our languages. So you can switch on a state. You can say, hey, based on, instead of, all these whens, you could instead switch on a state. So as it hide, wander, etc. And then internally, inside the switch, you can do when. You also can put a switch inside of a switch. You can do that too. But in this case, because only, one case or two cases, I chose to, use when and else when. And so perhaps this is a little bit more readable than the prior slide. Um, where instead of doing kind of all this whole thing, we're constantly writing, else when state equals, I could just write, switch. Perhaps it's a little better, but I mean, it's not a, revolution, but it's still nice. And yeah, the hardware should be, oops, gotta get the right, there we go. Yeah, the hardware should be similar, right? Um, cool. Questions? Okay, so yeah, so we can do state machines. That's pretty cool. So now you're starting to feel more comfortable with language. Hopefully you can do more things you're familiar with from other languages. So it's kind of run through a few scenarios. Number one, here I took the time to kind of sit there and think about running through a manual test. So I actually wrote out all these test cases to kind of do things with Raccoon. For example, originally keeping it noise outside so it stays in the hide state, right? At some point the noise goes away, goes to wander, etc. I'm going to critique my own code here for a second. Notice how for the action, I'm comparing against a uint. Here I'm comparing against the numbers, right? And the whole point of using enums was to have a single source of truth. And now I have two sources of truth, right? I have the numbers chosen in the test bench versus the numbers in the module. Um, the way to fix that is to declare your enum someplace else outside the module. And then that way your module can include the enum and your test bench can include the enum. And they can both get access to the same variables and same enums. So that's not what's done in this case, but I believe I did that for homework two's code, which we'll be seeing in a few days. And so you won't have that same scenario. Hopefully it won't be quite so ugly. But otherwise, you can see the test bench. You've seen these. It works. Okay, cool. Yes, the state of being hide. So if I go back to the code, this enum operation is going to assign things uints sequentially. So there's 0, 1, 2, 3. Now, I'm glad you asked that question because that reminds me to explain the syntax a little more. So you're probably wondering, what the heck is all this? And that's a good question. So what we've actually done here is constructed a list of variable names. And so this colon colon operator in Scala is the cons operator, for combining two things together. And so we've combined a bunch of things together, and then we've terminated it with a nil. Most of the time in this course, we don't really do list operations like this, so this is not super critical syntax for this course. But for now, you can remember this is just kind of boilerplate for when I want to declare an enum. I declare the variable names I want, like this. I put colon colon between them, and terminate with a nil, and then I gotta make sure this number here is the right one. So you can see why this is kind of very brittle. This is part of why they made that nicer chisel enum syntax, which you don't need to manually set number, you don't need to do colon colon. I wish the internet worked so we can kind of just show you. Oh, the internet may actually be working now. Great. Hey, okay. So um, let's go through this. Okay, so for the case of this one, it's amazing what the internet you can do. Okay, so chisel enum. Let's go appreciate that for a minute. Yeah, so for chisel enum, you can see that you do it via inheritance. So you extend chisel enum, and then you say the names you want to have. If you want to, you can set them to have a concrete value. And then later on, you can use this as a type, right? So in this case, you're using this inside a CPU to be a mux select. And so yeah, so then they declare this type to be mux select. And then based on that, you can now actually use that value. So you're actually doing a switch case in this statement based on the input, right? And you're actually able to kind of select from the two different options. Cool. And then from 20 minutes ago, see how we're doing in time, the question about reset, yeah, so it's implicit, right? But if you want to do things like having an asynchronous reset, you can actually just do it globally and set it all, or you can do various things, right? And so you can see there's kind of various types here um, and things in documentation. So maybe this is a good time for me to go to documentation for a second. So they did a nice job with the chisel. So there's kind of two levels of documentation. What you're seeing right here is what they call the cookbook, where they're kind of explaining various things. So for a particular language feature, it kind of has this prose that has a code example explaining what's going on. There's also a more traditional hierarchy document, right? So for example, uh, like this is your kind of more classic API kind of document, going through and generating all the methods and that kind of stuff. And so depending on what you want, I spent a lot of time with this one, but I imagine if I was learning this, I'd probably spend more time with this one, kind of looking more at the feature things on the left and kind of seeing how they match out. Cool. Yeah. Oh my gosh. It's amazing to have reset. Oh, sorry to have internet. Great. Yes. Question or? Okay. Cool. So we just did this raccoon example. Um, Other questions? No? Oh, you're saying right here. So right now we cannot do hide because it's not in the same scope, right? Because yeah, so this enum's inside the module scope. This is what I was saying a second ago, where if I did this better, what I would do is I would declare the enum inside of an object and have both the module and the test bench include the object, and they both can get access to hide. That would be the better way to do it. Yeah, correct. Yeah, you're right. But I mean, I think we could just copy paste that one line over. Um, yes, you could do that too. Um, yeah, and so copy and pasting the line, of course, runs the risk the two become out of sync. But I mean, I still think the copy and pasted line is better than raw numbers. So yeah, like I said, one of the things we can, of course, talk about code style and what makes sense and what's this is a good practice as well as what's readable, right? And so, yeah, I love these conversations, having things about how to make code kind of more clear and more robust. Cool, great comments. Okay, so as promised, we're now going to talk about, since we ran simulation, actually get something useful out of it. So um, I recommend, doing test-driven development, right? So you write test benches and you see, okay, originally I don't pass the test because things not implemented. Implement the thing, and then it should, of course, eventually pass the test, and eventually it kind of closes the gap. Um, what's good about tests is they're explicitly checking for certain behavior. A lot of times when you're writing a program or a hardware module, when you're first writing it and first developing it, you might just give it the minimal amount of stimulus to kind of make it do something, and then use a human, look at the output, whether the output be a printf or a case or hardware a waveform, but even software probably does. Looking at print output, oh yeah, it did the right thing, it printed the right thing. But you, the human, are checking that, right? And so, although that's helpful for day one for developing, after that, it's actually not as useful as you think because every time you want to see the thing is correct, you look at the output and remember what is the right value at the right time. Is that the right output? I don't know. Encode that memory, that information into a test bench. So, if the task passes, as far as you know, it passes this test, right? I don't need to remember when I run my module or run my program what order things should print in what way, right? That's what test is for. So like I said, number one, I recommend doing tests. However, for debugging or initial development, you want to look at the output manual. You want to actually look at stuff, right? So you have two choices. You have waveforms with the VCD file format, or you can do printing. And so I think it's kind of fun with this course, we mix of hardware and software students. Um, Software students tend to like printing, hardware students tend to like waveforms. I encourage students in this class to try and play around with both. Now, I would say when push comes to shove, I think students tend to use printf more than they should, and actually waveforms are pretty sweet. I would use them more. And so I've been working to try and make waveforms work inside the notebooks directly. It's not quite ready, but I think it's really close. So hopefully we'll be ready for tomorrow, the release with the lab, for lab two. Um, But I'm going to show you ways to look at waveforms even outside of Jupyter, which is a more common thing. Um, okay, so like I said, so both for waveforms and printfs, let's kind of talk about 2 ways of doing it, right? Um, and like I said, I think for most students, I think they tend to use printfs and they should use waveforms, but let's see that. Okay, so we'll talk about printing first and then close the waveforms to make this kind of a really cool finishing point. So for printing, it's important to think about printing in what way, right? So you, of course, can print in Scala when you're actually running your program. Remember, your chisel generator is a Scala program that's running, and there's this, side effect, this byproduct, which happens to be your hardware design, which gets passed on to generate fertile or whatever you're doing. So print line is a Scala function which will, print stuff out. And when it comes to what you put inside there, it needs to be a string. Scala has this ability to what they call string interpolation, or if you've seen Python F strings, right, where you can prefix the string with S, and then you can put the variables in there. So you want to put a variable in there, no problem. Or if you want to run a function, you put that inside curly braces, but before after $sign. So, for example, just a little bit of Scala. This is just pure Scala. Sure, right? I can define a variable, and I can go ahead and read it, or even call a method on that variable, no problem. So this is, as I said, this string interpolation works on strings. We're using your print line. Other places may use it even without prints, right? That's fine. So this is helpful, right? Maybe when you're debugging your generator, you want to know for some derived parameter what value the generator had. Print line's great. Okay, what about in the hardware? Well, let's remind ourselves what we're doing, right? So number one, in the actual hardware, you're not going to print anything, right? That's that's not going to be a thing. However, you might want to print things in simulation, right? So in the actual synthesized hardware, it's not going to be printing, but in the simulation, yes, you can print things, right? This is also true in Verilog as well. Okay, so for printing things in simulation, there's 2 styles you can do with Chisel. So they defined it as printf, which is actually not a built-in Scala thing. This is a Chisel thing. You can do it in the classic C style, where you have, what you call your format string, where you have a raw string and then, percent and then some specifier. And it's going to, and then you give the valid arguments here. This works. A lot of veteran programmers like this. I kind of like the interpolation style. So in this case, to do the interpolation, you have to put P first. But yeah, you can go ahead and have it, replace the variable in there. So this is going to be taking a chisel thing and printing this value in simulation. So for example, if we take our counter from before, and we go ahead and augment it to say, hey, we're incrementing it. So here, for example, they did the this is the printf C style. This is the interpolation style down below. So yeah, sure, this runs no problem. Maybe it's more clear when I do a simulation on the next slide. You can see the values of it, right? Hey, I have enable set to 1, and it's advanced time a bunch. It increments to 1, 0, and so you can see the appeal to printing, right? With printing, you can be very careful to print out exactly what you want to print. Usually, you want to put your print statements inside of a when thing to kind of control when they're triggered to kind of correspond to certain things. The semantics for print statements are they're printed once per cycle, right? So if you never advance time with dot step, you're only going to print once. So you're never going to see the other prints. And people think, oh yeah, I keep running my designs, peeking and poking values. And yeah, if you don't advance time, you're only going to see that first print. So it prints once per cycle if it's called, right? If print is, non-side of one, if that one condition is not true to that cycle, it's not going to print. You saw, for example, in this thing before, we have 2 print statements, but actually because they're, in exclusive cases of this when, we only get one at a time over here, right? Because we're either getting one or the other. Cool. Questions about prints? Okay. So, okay, this is the literals, and I'll close with the waveforms at the end. Yes, I'm still at time. Perfect. Okay, so for literals, these are, numbers. Sometimes you're going to want to express bigger numbers, and you want to do a way that's kind of convenient to you. Guess what? You can use different specifiers. If you want to do things in hexadecimal, it's not 0x like in a lot of languages, it's h in Chisel. So you declare a string, and then you have h, and then you cast it. You cast it to a uint. You can cast it to a uint of a certain width. You also can say dot as uint if you really want to. You also can put underscores wherever you want to break things up, make it more readable. That's all okay. Cool. Okay, let's go back to waveforms then. So like I said, waveforms are kind of a nice way to interact with things. So I had that early counter test bench ready to go. So how do you turn on waveforms in Chisel? The way you turn them on, we can put that back on, is there's two different places, but this is one place to do it, right here. So we call this test function. Instead we can call test, and we're going to add another argument. So rather than just being the module, we're going to pass an argument. So this is a seek. A seek is a Chisel list construct. You could possibly potentially pass multiple arguments, right? So in this case, we're choosing to pass the right VCD annotation. There are other annotations you may consider passing, right? So this is just one of them. Okay, so yeah, so in this case, we're telling it, go ahead and write the VCD file. So you may be wondering, okay, great, it ran. Where did that go? This is where we're going to go back to the infinity over here at the cameras on cameras on cameras. We can go inside the directory we're running in. This is probably the best one. So you can see, for example, when you're running stuff, it is, maybe I'll make this even bigger. It is generating, various files along the way. For example, Verilog files, like we were talking about. It's generating a .fir file, .fertile file. Not too relevant today, but there's, if you really care about the details of what's running, it tells you like more about the metadata of that thing you generated. But the thing we care about right now is this test run directory. So every time you run a simulation, it actually makes something inside this test run directory. And because I, preparing this lecture, ran these simulations a few times, oh my gosh, we have quite a few test run directories. So how do you find the right one? Because I get tired of doing this, I sometimes just keep nuking that directory, keep deleting that directory. That way there's only one there, so I know which one's the right one. But these are actually numbered by time. So if you want the newest one, it's going to be the biggest number. So it'll be this one. Okay, so let's go see what's inside that one. Yeah, so hey, guess what? Inside here, we have VCD files. We have a waveform file. So, okay, how can I view that? Well, if we go back to over here and go to our home page, under the tools thing, I have some references here. So number one, reminding you of how to do the simulation, but also for viewing the waveform, you have choices, right? So for most people and most platforms, the classic tool to use is GTK Wave, this open source VCD viewer. Here on my Mac, I'm about to launch a tool called Sequential. Just go ahead and do that, right? So you can see right now we're kind of following this step, right? So, okay, so trying out Scansion. Scansion is actually nice, but the problem is that it's no longer supported. And so occasionally it doesn't work because it's 10-year-old code. So we need to tell it what to run. So in my case, what I'm going to do is I'm going to just drag this waveform in there. Okay, we can go ahead and visualize that. So, okay, so now we have a waveform viewer. We're going to go ahead and add some waves to our view. So, for example, looking under counter, we can see, oh yeah, we can go drop a clock in there. We can go drop in reset. Maybe we want to see the IO input enable. Maybe we want to see the output, and maybe the count, right? Cool. So maybe you've all seen waveforms before from prior hardware design experiences. Scansion, is not too different than any Windows tools. It's just a Mac native app. You can go ahead and, drag around and see values. You, of course, can also, if you pick an individual signal, you can ask it questions like, oh yeah, go to the next time that changes, and that kind of stuff. So cool, this is Scansion. Like I said, it's available on Mac. I like it. It occasionally crashes horribly, or doesn't work because this code is unmaintained and I have a new Mac. So let's try the alternatives, right? So what are the alternatives? One of them is GTK Wave, which this is why I wanted internet earlier. I'm going to run it on my server. So I did install on my Mac, but I ran it on my server. So we can go ahead and say, hey, GTK Wave. I copied over to VCD file earlier. Great. And hey, here we are in GTK Wave, a popular open source waveform viewer. I can go ahead and, drop in my clock signal, my reset, and then once again, maybe I want to see the input enable, the output, and the count. And yeah, like any other, waveform you've seen, it has kind of these functionalities here. You can, zoom to fit. You can, select the signal. We'll do this one, say, okay, when's the next, change, etc. So for those from the software background, kind of wondering why I'm so excited about waveforms, right? Remember with printf, you are choosing when to print, right? Versus with a waveform, you were seeing the value of every variable over all time, right? So when it comes to debugging, rather than, looking at some print statements and going, oh, shoot, I want to collect that data and run it again with more print statements, you run the waveform once and you look at the same waveform and keep crawling around until you see the information you want and you're done. So you kind of get it all in one shot. Now, there's some trade-offs, right? You can imagine the waveforms get really big because it's all values over all time. Fortunately for us in this course, we usually don't run simulations very long, so that won't be a problem for us. If we're doing like a process development, you want to run 1 billion cycles, yeah, these are a problem. But here we're running, at most dozens, hundreds, maybe thousands of cycles. Don't worry about file sizes, it's not a problem. But even if it's not a file size problem, it's still a wall of data, right? That's why sometimes you gotta be a little bit better about finding what you want inside the waveform. So for example, like I said, using these functionalities to say, hey, when does this value change? And using, this value should be constant, but when's it change next or whatever? These things kind of help. In contrast, the printing, right, I think is most powerful when you're using it sparingly, right? When you have a longer running simulation of a lot of values, and there's only a very certain case you want to know what happens, right? And so rather than spending, a lot of time digging through, 100,000 signals on a waveform, you want to know exactly when that condition occurs. You can kind of write that one and say, okay, well, when A and B and not C, I want to see the value of D, and you can print that out. This is kind of that trade-off. To close out on the waveforms, I also wanted to show another option. So a lot of students love using VS Code. So yeah, someone actually made a VS Code plugin called Wavetrace. So we recommend that if you want to go ahead and give that a whirl. Another fun one is actually there's a completely web-based one. So I'm going to have to go ahead and exit this to make this a little easier to launch. But if I go ahead to this, it's a website. So you simply just drop your VCD file into it, and boom, we've got VCD on the website. So this is pretty cool. The same developer is a sci-fi engineer, and so I've been using his other project to try and incorporate waveforms directly into the notebooks, and that way you don't need to launch any other programs. But pending the Jupyter waveforms, especially for homeworks, which are going to be much bigger and you aren't going to be in Jupyter, you just want to learn how to use one of these tools. So whichever one of these floats your boat, whether it be, GTK is probably the simple, safe choice, but maybe you're using VS Code, you want to use the Wavetrace. Maybe you're on a Mac and you want to keep a Mac native app and you want to try out Scansion, or maybe you're happy to web one. That's fine. This web one, like I said, you can, you can zoom scroll and that kind of stuff. It's a nice little JavaScript thing. Cool. But I recommend definitely using waveforms, and I'm trying to get this waveform thing done in time for lab 2. So it's a good reminder for me to put out there for folks. As a reminder for the assignments, we have lab 1 due tomorrow night. I recommend getting the labs done early, just kind of get them on, move on, next thing. Homework 1's due Sunday. Going forward, we're going to try to get to the cadence of hopefully having labs due on Tuesdays and homeworks due Sundays. I say hopefully, because eventually assignments start getting longer. We may kind of stretch the deadlines a little bit, or maybe it'll be a bug and I'll give an extension or something like that. So it's a little bit in flux, but the ideal cadence will be roughly one lab, one homework per week. Hopefully the lab you can do in an hour or at most an afternoon, and put you in a good position to do the homework, which is a longer form thing. Great. Any questions? Cool. Well, that's all, folks. Have a good day.